Alright, so in this video, we will be talking about the comparison test. There are two comparison tests that you need to know. So the first one is the direct comparison test, and the second one is the limit comparison test. And as you can see here, we have our basic things that we need to know for the test, and I will explain it more in depth. So in direct comparison test, you need two series. So the series of AN and the series of BN. And the series of BN must be greater than the series of AN. For the limit comparison test, you gotta do the limit from n to infinity, AN over BN, absolute value. And you will have to find the coefficient of that. But let me explain it more better while showing examples. So before we get into this, I want to let you all understand what P series is about. So let's say we have like a series, right? And in the denominator, we have a number with an exponent, that's P. And if the P is less than 1, less than equal to 1, then the whole series is divergent. But if the P is greater than 1, then the series is convergent. So that's just something that you will need to know for this topic. Let's say we have a series that contains A, which is the coefficient, and R, which is the common ratio. If the R is less than 1, the whole series is convergent. But if the R is greater than 1, then the whole series is divergent. So make sure to keep this in mind. So here we have our first step for this problem. We're going to rename it. So we name it to AN to find the BN because let's say we're going to use the limit comparison test, right? And we know the equation for that is AN over BN. So we need to find a BN. So our BN would be something simple, like it doesn't have to be crazy. So we could just use what we have from the AN and we can just turn it to the BN. So our BN, we could have it be 1 over N. So because the BN is supposed to be less than the AN, because when we do our comparison, the AN is supposed to be less than the BN because the BN is supposed to be greater than AN. And when we do this, we had to put only one denominator for BN because let's say that if the denominator for AN has like is bigger, then the whole thing will be less. And if it's just 1, then this will be bigger. Then it will be greater than the other series. Because if you have like a lot of things in the denominator, then it will make the whole thing less. And if you have more, like less things in the denominator, it'll be, not that much less, but it will be still greater than the other series. So make sure to keep that in mind. The BN is supposed to be greater than the AN. So now we have to plug in our equations. So it would be the limit from n to infinity, AN over BN. Plug in your values at this point. So this would be 1 over 2n plus 3 over 1 over n. And we can multiply the reciprocal of that, so it would just be n over 1. And here we got n over 2n plus 3. We have to find the first coefficients of the value. So in this case, we have n over 2n plus 3. We have to find the coefficients that will make it the number. So in the bottom we have 2, but in the top, what do we have? It will be just 1 because that will make it more reasonable. So this would just be 1 over 2. Another way you can do it is, you know how we did the when we take the integrals or when we do the series, we would just like divide it by n or the highest denominator exponent, in which case it's n. So this would be just dividing by these n's. So it would just lead to 1 over 2. And so in this situation, it would be divergent. Because if we use p series for these, this will just be the exponent is just 1. So, and remember, if the p series is less than or equal to 1, then it is divergent. So this would be divergent. But you need to show this worked as well. So we could say by the limit comparison test, since the series of 1 over n diverges, which is Bn, then the series of 1 over 2n plus 3, which is An, also diverges. So this would be therefore divergent. Alright, so we have another problem. In this case, we are going to use a geometric series. So let's start off by rewriting this. So we can rewrite this to An. And n is supposed to be less than or greater than the An. So we can just take out the 3 plus 3. So this will be 9 to the power of n over 10 to the power of n. And we can rewrite this by just putting the exponent just putting 9 over 10 and the exponent of n, because when you think about it, when you distribute that exponent, it's basically the same as 9 to the power of n over 10 to the power of n. So we have our Bn over here. And then we can use our geometric series because we have a common ratio, which is 9 over 10. And we know that if r is less than 1, then it converges. So this converges. So the Bn converges, then the An converges, which makes everything converges. So that's the answer for this question. So your answer will look like this. Since the series of Bn converges, An must also converge by the direct comparison test. It will look something like this, but you can maneuver it however way you like. So here we have like a natural log function for a series, and we're gonna do the same thing. We're gonna rewrite this to An because this is the smallest series. So, and then we have to write it the Bn, and we can use 1 over n for for this equation because 1 over n would be greater than An, so just be 1 over n. And for this equation, and for this problem, you could just literally just use p series. So the p series here, it will just be 1 here because it's to the power of nothing. So if you put it to the power of 1, it would just be the same number as it was before. So the p series will be equal to 1. And we know that if the p series is less than or equal to 1, then it is divergent. So therefore making this problem divergent. And you can write it like if Bn, but the Bn is divergent For A1 is also divergent by the P series. And that's pretty much it for this problem.